Hi, I'm Chris Salvino, the CEO of Lunar Helium-3 Mining. The discussion today is entitled Helium-3 Mining, the Tip of the Spear for Lunar Economy. Another way of looking at this is we believe the extraction of helium-3 from the surface of the moon will allow for the building of the most profitable, sustained, commercial space infrastructure in history. This is a non-NDA version presentation. The singular focus of our company LH3M is to extract helium-3 from the surface of the moon. This helium-3 is very important. We'll be talking about that today. It has existing uses such as cryogenics and neutron detection. There's large upcoming future uses such as nuclear fusion reaction. When you use helium-3 in nuclear fusion reactions, that will become the world's first true green sustainable energy source. In addition, quantum computing is extremely essential for national security. Without helium-3, you cannot cool quantum computing down to the level it has to be at 0.01 Kelvin. My background is somewhat eclectic. It includes medicine, but also more importantly, for the respect of this presentation, this includes everything from planetary geology to mechanical and aerospace engineering, flight test engineering. Really important topic is engineering mining, how to extract minerals off the ground, along with aerospace medicine. The agenda during this presentation will be fast-paced. I'm going to talk about why should we even go back to the moon, a very important fundamental question, where you can get helium-3 from, existing cases of helium-3 and future cases of helium-3 that we talked about in an earlier slide. An important topic, revenue projections, especially for investors, the challenges of extracting helium-3, and then some slides about our company. So the question is really, why are we going back to the moon? I respectfully feel this question has not been answered fully. Is it for a cost center reason, such as scientific research, global competition, Mars preparation? Are we mainly going to the South Pole to extract water, in which geologists have a very good feeling that it's already there? Those ideas are laudable. They are cost centers. These objectives require continuous funding but do not generate sustainable revenue. If we take a look back at Apollo was supposed to have been 20 landings to the moon. Only 6 took place back in an era when the United States was not so much in debt, and back in an era when Apollo captured the world's and the US population's attention. So cost centers may not be the primary reason to go back to the moon. However, the good news is we believe there's a revenue generator, not a cost center reason to go back to the moon. That's to extract helium-3 from the surface of the moon for commercial purposes. This is an estimated to be a multi-trillion-dollar a year industry when fully implemented. We'll be talking about that in the upcoming slides. Helium-3 is an isotope of helium with 2 protons, 1 neutron. It's non-radioactive, it's extremely rare, and it exists as a stable gas. The most important thing to note about helium-3 is it's very unusual. It has very special use cases on Earth, which we will dive into deeper. So where do you get helium-3 from? On Earth, it comes from the decay of tritium from nuclear weapons production, specifically from the Cold War. The estimated US supply is almost exhausted at less than 10 kilos, and I must emphasize that it's almost exhausted. It comes from the sun also. It can travel with the solar wind along with helium-4, and it's captured on Earth by our atmosphere, so it does not really get through the atmosphere. It's very rare. On the moon, there's no atmosphere, so helium-3 has been baked into the surface of the moon called the regolith over billions of years. The good news is it's estimated to be about 1 million tons of helium-3 on the surface of the moon. This could be more or less, but still a lot. The sort of difficult news or news that has to be dealt with when it comes to extraction is many people believe that the concentration of helium-3 ranges between 1 and 15 parts per billion. It's a small number. So a little bit deeper dive. Helium-3 on Earth comes from a byproduct of nuclear weapons production. At one point there was about 20 kilograms or so of helium-3 in the United States a few decades ago. As we mentioned, mining is impossible. It is possible to produce this in a type of fusion reaction, but the yield is low and scaling appears to be impractical. So the only true source within reason to extract helium-3 is on the surface of the moon, again with a rough estimate of approximately 1 million tons. Now, how is helium-3, which comes from the sun, retained in the regolith, or the surface of the moon? We believe and hypothesize that it could be a number of different ways, potentially a combination of all of the above. Number one, primarily comes from the solar wind from the sun. Therefore, the energy when it hits the surface of the moon is extremely tiny, so it's most likely attached loosely to the grains of the regolith at the surface. During the bombardment of the moon, which was billions of years ago, the high portion of bombardment, there was a lot of energy with these impacts, and so helium-3 may be related to crystals or other minerals from that impact billions of years ago, and potentially could be more at depth. There's also discussion whether this could be chemically bound or chemically related to other minerals such as ilmenite, but this hypothesis is based on some Apollo data, which is sort of iffy. We believe as a company that the bulk of the helium-3 is mostly at the surface, with a smaller portion, much smaller portion deeper down into the regolith, as far down as 1 to 3 meters. Let's discuss present use cases of helium-3. There are existing cases for helium-3 in the United States now. They are outlined in the left-hand column, and the most important is radiation detection for border security, looking for bombs. If you look to the second to the last column on the right, let's look at the amount of helium-3 that was used in the United States in 2008, about 15 years ago or so, compared to roughly the present. Even though it says 2010, we don't have actual numbers. The whole idea of this slide is to look at trends. So about 15 to 16 years ago, the amount of helium-3 used in the United States was roughly 1 kilogram. These are rough numbers, but since the supply has dwindled, the amount of helium-3 available for use has dropped to probably about 1 kilogram or less. So even border security has been reduced when it comes to the usage of helium-3 because there's just not a lot of helium-3 left. Okay, let's look at future use cases, the two big things. First one is nuclear fusion. Here's a fundamental question. When you drive an electric car or go on an electric train, is that green, that vehicle green? It really depends on where the electricity comes from. So if the electricity comes from a coal or nuclear fission plant, no, it's not green. Ultimately, we believe we'll shift over to nuclear fusion, which we will talk about. And the question for nuclear fusion is nuclear fusion with its existing future fuel source of tritium green? These are some questions we're going to explore in the next couple of slides. The present source of electricity across the globe is mainly coming from fossil fuel nuclear fusion. Many people know the downsides of fossil fuels such as coal and gasoline. It produces a huge amount of carbon dioxide. In fact, it could fill up essentially about 10 million Olympic-sized pools worth of CO2 every year. This does cause global warming to some extent from human consumption and production of electricity. When it comes to nuclear fission, the cons there is that the waste has to be stored for up to 100,000 years, and even the United States is not prepared for this. There's no massive storage centralized facility in the United States, let alone one that could last to 100,000 years. The other big thing is nuclear fission is subject to catastrophic explosions and storage issues. All we have to do is look at Chernobyl to see that as an example. Okay, so looking into the future source of electricity we believe will be coming from nuclear fusion, not to be confused with nuclear fission. Fusion is a reaction in which two or more atomic nuclei combine or fuse under extreme temperatures, releasing lighter particles and ultimately energy. So hopefully more energy comes out than goes in. There's two major reactions to be aware of. That's between deuterium and tritium. That produces helium-4, a neutron, which is why I put that in red for N, plus energy. Our company has coined the term fusion 1.0. The second reaction is deuterium and helium-3. That produces helium-4 also, and this time a proton and energy. We've termed that fusion 2.0. The pros for both types of fusion 1.0 and 2.0 is fusion cannot explode, which is a huge advantage over fission. Nuclear fission 1.0 is right around the corner. There is a commercial contract signed between a company called Helion and Microsoft to produce some entry-level amounts of power or electricity in 2028. It is estimated that mass production will begin and mature over the next 10 or 20 years. Again, we predict fusion will replace nuclear fission and fossil fuels in the future. However, let's dive down deeper into fusion. Again, looking at fusion 1.0, which is using tritium, and 2.0, which is helium-3. The bulk of the development, as we will see, for fusion going into the future is with tritium, because fusion companies do not realize that it is possible to obtain helium-3 off the surface of the moon, because they also know that you cannot obtain it from Earth. So rightfully so, they're building their fusion reactor developments using tritium at the present moment. There is a significant difference between these two, as you can see in these two columns. Fusion 2.0 with helium-3 is scalable. No one really knows how to scale the tritium production and breeder blankets at the present moment. With tritium, you have to store the byproducts for up to 100 years. Tritium has more reactor damage. It's more dangerous for humans. But ultimately, if you look at the green column, helium-3 is scalable off the surface of the moon, does not require the storage of byproducts, does not cause nearly as much reactor degradation, is less dangerous for humans. And if you look over into the oval to the right, ultimately, helium-3 for the general public should be perceived as the world's first true green energy source. Again, can't explode, no byproducts for storage, relatively safe, and because of that, we can envision a time in the future in which there may be fusion reactors for your house, your car, a semi-truck, or a small city. With respect to development so far, if you looked in the left-hand column, Fusion 1.0 with tritium, there's been billions of dollars spent by more than 40 companies in more than 10 countries on this. It's maturing fairly rapidly. The thing called TRL is an acronym in certain types of engineering called the technical readiness level, between 1 and 9. 1 is sort of an idea, 9 is a fully implemented commercial stage. So fusion is advancing. The usage of helium-3 and the extraction of helium-3 off the surface of the moon is more like in its infancy and still, in many respects, at the discussion stage or early development stage. We've had sample returns from Apollo, from Russia, from China, that have shown helium-3 in samples. Governments, specifically China and India, have talked about going to the moon to extract it, and there are private companies such as ourselves and a few others looking at helium-3 extraction from the surface of the moon for fusion. Let's take a broad stroke numbers. Make the assumption that nuclear fusion eventually makes it across the globe to produce all electricity. And also make the assumption that helium-3 comes off the moon and is the only fuel source for fusion. Fusion in general is estimated to be a $40 trillion industry as it replaces the burning of fossil fuels and nuclear fission. So it's going to replace one for the other. That's not a new $40 trillion valuation. Well, if you powered all of these reactors using helium-3 as the fuel source, you would eventually need about 570 metric tons of helium-3 per year, which is a significantly small microscopic fraction of the volume of coal that's needed if you use coal to power electric plants across the globe. Let's now look at the second major use case for helium-3 in the future, quantum computing. Quantum computing is still experimental, but it's advancing rapidly, and I love this example. If you took a classical computer and gave it an equation or a line of numbers, if the line of numbers was 2048 in length, and you try to break it down into its prime components, that calculation would take a classical computer 10,000 years to do, but a quantum computer can do that in less than half of a day. That is so different in speed. Potential applications are mind-boggling, from cryptography to drug discovery, potentially cures of certain forms of cancer. But politically, we should pay attention to this because it can allow for major geopolitical strategic dominance. Can you imagine if China had quantum computers over America? Now, what does this have to do with helium-3? It's not a fuel source. Well, helium-3 is used to cool quantum computers down to about 0.01 Kelvin. Without them being cooled down to that temperature, they don't function correctly. There is no other way of cooling quantum computers that is known at the present moment without the usages of helium-3. Now, how much helium-3 would quantum computers use as a whole? Well, roughly a quantum computer is estimated roughly to use about 1 to 10 liters of liquid helium-3 for cooling. No one has a great idea how many quantum computers there might be, so if we estimate it in about 15 years, there may be 10,000 quantum computers in 15 years. The total helium-3 demand for 10,000 computers would be about 4 metric tons. Let's try to put the nuclear fusion with helium-3 and quantum computing in perspective when it comes to revenue. Very important slide. Today's helium-3 prices are roughly $30,000 a gram, or $30 billion a metric ton. Future helium-3 prices will most likely be dictated by market conditions. Helium-3 must remain reasonable to compete with fossil fuel usage, such as to keep your electric bill within reason. So yes, we do believe this will fluctuate. We actually think it will go up for quantum computing and then eventually come down, most likely for electricity. However, the numbers are still staggering. If the world needs 570 metric tons of helium-3 plus another 4 for quantum, you're looking at a massive revenue stream of about $17 trillion in today's dollars. And quantum computing, I sort of combined that last statement. Quantum computing for 4 metric tons would need about 119 billion, still a very respectable number. So the revenue stream off commercial production of helium-3 is staggering in the trillions of dollars. This represents a large subset of the total nuclear fusion industry of $40 trillion, as we mentioned on the last slide. Now let's talk about helium-3 and extracting this off the surface of the moon. What does the competitive landscape look like? If you look to the right again, that technical readiness level, TRL, means this is still kind of an early stage, but it's important to discuss who's talking about helium-3. China has returned, as we mentioned, some small samples demonstrating helium-3, just like Apollo did. They've announced their intent to extract it. They are far along with their space program, in many respects on par with the United States. India has expressed an interest of extracting helium throughout the surface of the moon. They are farther behind, but they're the up-and-coming player to watch out for. The United States has no public position on the extraction of helium-3. They are still focused on going to the south pole of the moon to extract water and to do some mineralogy and research. There are private companies that have discussed extracting helium-3, and including ours. We believe we have a competitive edge. As we will discuss at some point, our approach is to work with the moon's environment and not against it. That sounds like a general topic, but it's an extremely important one. I will be giving some examples in this presentation coming up. Specifically, we've come up with a low energy extraction process with the least amount of moving parts, and that will become more relevant on what this means in a few slides in the near future here. And we also have a very strong IP portfolio. I believe this is probably one of the most important slides in this presentation, if not the most important slide, specifically also for those looking to invest. The success triangle is a term used many times in the mining industry to describe positive return on investment. We believe that three things must take place for a positive return on investment from a broad picture point of view. Number one is there needs to be a reduction in transportation costs to the moon and back, similar to what's taking place with the cost of low Earth orbit transportation for satellite deposit. Second is the commercialization of nuclear fusion and the switching over to nuclear fusion with helium-3. And third, which we will spend some time on, and again, it sounds kind of nebulous, but it's very important. You have to extract helium-3 off the surface of the moon using lunar techniques and not Earth-based techniques. So the success to make money off the lunar surface for helium-3 is going to be reduction in transportation costs, commercialization of fusion, and the coupling of this with the extraction of helium-3 using lunar-based techniques. So do you think the future of lunar mining looks anything like this? Well, this is a typical open pit mining process on Earth. This happens to be an Australian gold mine. The typical way to get precious resources out of the ground is by grinding or blasting the ground, taking the blasted ore, processing it by making it smaller, then heating it or chemically treating it to extract out the resource, in this case gold. And at the back end you shoot out all the wasted rock, which is called the tailings. This is an earth-based process, and it works when you have concentrations, for example, like copper of 0.4%. So the question is this process applicable to the moon? So keep that last slide in mind. This looks more lunar. This is no one particular company's simulated mining rover. This is something we have created, but it's based on Earth-based principles. So this theoretical future mining rover on the surface of the moon in the front has that round thing called a bucket wheel. That is a standard way of grinding the ground on Earth. That bucket wheel then grinds to the ground or grinds down to a certain depth. The material comes up on a conveyor belt, goes inside, and then theoretically you would chemically or heat treat this. Now this is a Earth-based mining technique. There's a lot of energy involved in extracting the ground and getting the ore out of the ground. There's a lot of moving parts. So the last slide and this slide are basically the same, even though in many respects they look very, very different. This process, if used on the moon, we predict would not work correctly because of the energy of extraction and the amount of moving parts. And for bonus differential, the moon has virtually no atmosphere, so anything that is gaseous that might be liberated during this process would go shooting off into space. So bottom line is the last slide and this slide look different, but they're the same theoretical way of extracting precious resources out of the ground. And oh, by the way, out the back end of this lunar rover, the wasted rock called tailings would be shot out the back end or dropped out the back end, and you would hold on to the precious resource, whatever it happened to be. Okay, we're now going to talk about some challenges. We're not going to get into all of them in the interest of time. Just a couple to show how the moon's environment is so different when it comes to the mining process. First challenge happens to be the concentration of helium-3. The good news is, I mentioned, there's a rough estimate of 1 million tons of helium-3 on the surface of the moon. Whether that's perfectly accurate or off by 50%, it's still a huge amount. So the good news is there's a lot of it. The bad news is its concentration is very low. An estimated 1 to 15 parts per billion. We actually think it's a little bit higher than that. But this compared to an Earth copper mine, for example, at 0.5 parts per 100, is very different, way low concentration. If you use those standard Earth-based mining techniques I just showed you, in which you actually have to spend a lot of energy to extract the ore out of the ground, the energy equation is basically just not practical. You would need to actually grind up 999 parts of ore out of the ground to obtain 1 part of usable helium-3. So you would get 1 part of usable helium-3, and you would dump out the back end, theoretically 999 million parts of unusable tailings. This is, from an energy point of view, very costly, not practical. Our solution is to understand this concentration issue and create a lunar, unique, low energy extraction process designed for the conditions on the surface of the moon. Second challenge is that the lunar dust is not Earth-based dust. Lunar dust has never been eroded or smoothened by wind or water because there's never been flowing water or wind on the surface of the moon. Consequently, lunar dust looks the same as it did billions of years ago. It's sharp and spickly. It looks just like that microscopic image to the top right. It's 45% in silica. It's charged from solar radiation, so it can levitate above the ground. It's magnetized for a number of different reasons. There's iron involved. And ultimately, unlike Earth-based dust, it's extremely abrasive and extremely clingy. There is a paraphrase comment from Gene Cernan from years ago from Apollo 17. He basically said something like this, that I think we can overcome other physiological, physical, and mechanical problems except dust. He was trying to tell us that this is probably the most critical issue to overcome if you want to survive and live on the surface of the moon. Let's take Gene Cernan's comments and let's look briefly at a snapshot from the past. Apollo 17 in 1972 was the longest human mission on the surface of the moon. There were 3 EVAs totaling 22 hours outside the lunar habitat. During that short period of time, it did a huge amount of damage. It destroyed vacuum seals, eroded 3 out of 12 to 15 layers of one of the astronauts' boots. It compromised shoulder movement and basically adhered to virtually everything. As you can see in the image in the photograph, that's all lunar dust in its spacesuit. We cannot go to the moon and use Earth-based techniques with numerous moving parts. We believe that's a setup for failure. We recognize this, and we've come up with a mining process that we believe will have minimal moving parts to help minimize the chances of breakdown. Another small challenge, or a challenge, that has to do with loose rocks. Our mining technique requires us to develop a semi-contained seal underneath our mining rover because gases such as helium-3, they get liberated out of the ground. Sometimes you can liberate it with heat, and sometimes you liberate it just by moving. But these gases that are loosely bound to the regolith, if they are disturbed, they go shooting off into space because there's no atmosphere. That's why you need to mine and protect the gas from going shooting out. Our way of doing this is to have a skirt that goes around the rover that, as much as possible, will contain these gases before they could be lost. To minimize the disruption of this thermal skirt, we want to minimize loose rocks that go underneath the rover. Now, we're not going to be able to stop all loose rocks, and the thermal skirt will be pliable to that. But as much as we can, we would like to move the rocks around and behind the rover so they don't disrupt the mining process as much as possible, and they're not pushed over into the next lane coming up like a farmer's plow. So we've come up with a proprietary technique in order for the rocks to be moved around the rover and not underneath the rover. Here's another view of that. It looks like a bi-directional unusual snowplow. The rocks will impact the plow, which is bi-directional in the front. They'll be directed around, if you look at channel 2, and out the back of the rover in channel 3. This will not be perfect, but it will reduce as much as possible the containment skirt from being moved much. Okay, I've only touched on a couple adaptations needed to take place. We mentioned concentration of helium-3, the abrasive nature of the regolith, the fact that we are in no atmosphere, it's basically virtually a vacuum. There are more, but in the interest of time, we are now going to switch over to some things our company did. When we formed a couple of years ago, LH3 was given a mandate, which is our company, to work with the moon and not against it. Again, it sounds simplistic, but it's very, very core to how we set up our systematic systems engineering approach to the moon. We have a group of diverse minds. There's not a vertical aspect to our collaborative innovation. It's all horizontal. Everything from engineering, mining to aerospace engineering, geology, work in austere environments, medicine or space medicine, systems engineering, nuclear physicists, energy scientists, and other disciplines that if we haven't added, we will be adding at some point. Ultimately, no one can particularly understand the moon at the present moment. We at best think we understand some of the moon. We've tried our best to use these disciplines to bring their knowledge together to understand the moon from a mining point of view as best as we can in today's world. From an outreach point of view, we presented at a number of different conferences, probably 10 or 15 just in the last 6 to 7 months, everything from critical minerals conferences to fusion, quantum, policy, and green energy conferences. We have grant applications in process now, and we're working on much bigger grants coming up over the next couple of months. We've had significant strategic discussions with small to large aerospace companies on grant applications together, missions, and other types of relationships, including financial. Our patent portfolio includes 10 issued patents, 10 pending patents in the United States, more in development, and we also have an international pending portfolio that's growing. The singular focus of our company, as we mentioned before, is solely on the extraction of lunar helium-3 and economically return it to Earth. We believe we are the only company in the world to be singularly focused on doing this. We attempt to understand the environment. We've created a diverse team. We're using a systems engineering approach. We've adopted first principles. And if you look at those 5 steps, this is where we focused, targeting the surface and subsurface, how to heat the regolith with the least amount of energy, to direct the gases and not let them get lost, then to separate them and to concentrate helium-3 down into a form which is going to be liquid to return that back to the surface of the Earth. As we've mentioned before, we are continuing to work advancing our technical readiness level, building up strategic partnerships, and applying for larger grants in the near future. We believe the business strategy case from idea up through commercialization, revenue, production can be broken down in 3 major phases. Phase 1 we have completed. We've completed that on time. We've been internally funded with no debt. That's been basically focused on developing a very important, robust IP portfolio. Second is where we've entered now, is phase 2, expanding capabilities and partnerships. We will expand our IP portfolio, work on larger grants, hardware development. We've already begun working on major strategic partnerships, and we'll begin looking for funding appropriate for this particular phase. This will include work on Earth with development of hardware and eventually going to the moon for demo sorts of missions and return samples. Phase 3, commercialization, is once we scale up for production and return back for revenue generation. Eventually, we believe there'll be more than 100 or so commercial autonomous rovers on the surface of the moon with humans to support the process and to fix broken rovers. This is a point in time when there will be a positive return on investment, initially from strategic quantum computing, and then as fusion builds out. Okay, this is an important slide. We've been in discussions with multiple large, medium to large space companies, And we had discussions about synergy. I think this is important for anybody who's looking to invest or just understand our strategy. Our company intends to focus on the tip of the sphere, which is the extraction of helium-3 out of the surface of the regolith on the moon. So LH3M wants to focus on everything under a rover. We need these other space companies to run interference, to work with other companies, to work with federal governments. And so we're looking for other companies to help us facilitate the other parts of the infrastructure. That slide is really important because it tells you that we are trying to stay focused on what we know best, but there's going to be infrastructure that must be built. And there's other companies that are obviously much better at this than us because they've been doing it for quite some time. So in summary, building a lunar economy, here's some of the summary topics. The core objective is helium-3 should be mined off the surface of the moon to power Earth's future green energy and computer systems. This will drive the need for a sustainable lunar presence that is based on a positive return on investment. This will require significant supporting infrastructure, such as transportation, additional equipment, personnel, and again, strategic partnerships. This is a massive, monumental undertaking, but just like the Manhattan Project or the Apollo Project, this is something that is definitely obtainable. And a final summary here is that there's an estimated roughly 1 million tons. Whether it's exactly 1 million tons or not, no one knows, but there's a lot of helium-3 on the surface of the moon. The two use cases we discussed are fusion 2.0, that's a combination of helium-3 and deuterium. That is the preferred fuel for fusion. If fusion is adopted worldwide with helium-3, you need about 570 metric tons. In today's dollars, that would be $17 trillion with a T. It's a huge amount of revenue. From a quantum computing point of view, this is a strategic need. These are a rough estimate of 10,000 quantum computers in 15 years, and that would be about $119 billion worth of revenue. As I mentioned earlier, the key to success of extraction from a positive return on investment would be the reduction in transportation cost, worldwide commercialization of fusion and adopting of helium-3, and as I've really emphasized a lot, and it's in red there for a reason, the usage of lunar-based mining techniques, not Earth-based mining techniques. Our company, as we mentioned, is singularly focused on extracting helium-3. We may be the only company only doing this. We are attempting to understand the lunar environment and use a systems engineering approach to extraction of helium-3. We are in the process of adding larger grants. From an application point of view, we've been working with strategic large, medium space companies, and we'll be looking for larger funding in the near future. The tip of the sphere for lunar economy, we believe, is solely the extraction of helium-3. This will drive the development of infrastructure, and there'll be plenty of partners needed to create this level of economy on the moon.